Alright, so this is going to be our notes on fluids. And so far we've talked about pressure, absolute pressure. We've talked about different principles such as Archimedes' principle and Pascal's principle. And today we're going to kind of flesh this out a little bit more and talk about a fluid. Now you can see here, a fluid is any non-solid, so cannot be a solid. Okay, that has the ability to flow and change shape. So we know this ability to flow, that's either a liquid or a gas, because they can flow, right? We can pour something out of a glass of water can flow, but so can a gas. You might not have thought of this before, but a gas can also have flow as well, and the gas always changes shape, and so does a liquid. So if you have a glass and you pour the water into it, it then takes the shape of the container. So if we have water here, let's just make it blue. Right, so we have some water in here, but if we took that same water and then poured it into a different container, so if we change the container and we made it like a long container like this fluid that we poured into this water would then take this shape instead. Be a completely different shape, right? It'd be flat on the top. I'm just kind of learning how to use this pen, but you kind of get the idea. So takes the shape of the container. Now if we have a gas, so if we have like a little container here, something that looks like this. Let's say we made a little special container. Like took a flask, turned it upside down, and then we put a gas into it like oxygen. Okay, we had a little thing here, a little valve, and we opened it and we put some oxygen into it. This would then have oxygen molecules, and it would be just taking the shape, not really taking the shape, but it would be changing the shape of changing its own shape. It wouldn't be taking the shape of the container, but it'd be bouncing around, and really it doesn't have any shape at all. So so a liquid or gas fits both. They can flow, and if we wanted to, we could take this container, actually the flow part, we could take this container, and if we thought about, opening it up, we could probably get this oxygen to flow out, even though it is a gas, so it can flow as well. So a fluid, in reality, it can be a liquid. We usually think of that, but it can also be a gas, because these are the two main ideas that we have to define whether it is a fluid. Now there's some basic properties of fluid, and something that really is important, not just for the fluid, but for the thing that goes into the fluid, is something called density. And density is just mass per unit volume. So how much volume does it have, and how much mass? Okay, a good example of this is lead. So if we had a little cube of lead, if we could go to the store and buy a cube of lead, PB, and it was 1 by 1, maybe 1 centimeter by 1 centimeter, and it was a cube. So we'd go, this size here, there. I'm just trying to make a cube. So we could then, we know it's 1 by 1 by 1, so it'd be 1 centimeter squared. That would be its volume. And then if we put it on a scale and we weighed it, we might see it weighs 50 grams. If we took a different substance, such as aluminum, Al, and made it the same size, 1 by 1 by 1, so let's see if I can do this. My drawing skills are not the best with this. So if we made this thing here, it's a little bit better this time actually, and this was a 1 by 1, it would have the same volume, 1 centimeter squared, right? Because if it was 1 by 1 by 1, right, these are all the same, it'd be 1 centimeter squared, right? Actually cubed, I don't know what I'm saying squared for. 1 centimeter cubed, be the same. So these are the same size, but if we then took the mass of this, we might find out that this is 5 grams. instead of 50. It might be 1/10 of what this is. And that's what density is talking about. How much do you have and how much mass does it have? And some things are much more dense than others. Solids is pretty obvious. And this all has to do with how tightly the molecules are packed, because solids have a crystalline structure. So some are really close together. Some are a little bit further apart, even though they're a solid. So depending on how many molecules you have packed together in this certain amount of area, that's going to give you more mass, but you might have the same volume. So that's kind of what density is talking about. So we compare the mass, we divide the volume, and it gives us the density of the object. Lead, very dense. Lots of other objects that are the same way. Some are very light. Aluminum's very light. If you think of like lava rock, like pumice, very dense. If you think of iron, it's pretty dense as well. So some things are dense, some things are not so dense. The unit for density that we're going to worry about is kilograms divided by meters cubed. So this would be an even smaller number. But that's what density is talking about. And in a fluid, it can also have different densities based on how many different molecules and what are the molecules contained within that fluid, whether it's a liquid or a gas. Okay, so let's erase all this stuff. And if we continue, I'm going to move this down here. So that's the first one. Density is a property of a fluid. We also worry though about density, and you're going to you've been looking at this in lab. So if we have a swimming pool, let's say, and we have some water, go back on that one. So if we have some water in there, let's kind of go here, and we take a block of lead and we place it in here, PB, it's going to sink, right? Because it's more dense than the water itself. Because the density of water is just based on what's its mass compared to its area. And water has this ability, so if you place something in the water, like let's say it was a block of wood, okay, it would probably float. What causes this to float is this the idea that there's forces acting on this block. Because if the only force was acting on this was the force of gravity, it would have to sink, because the gravity would just pull it closer and closer, and it would sink. So that tells us if this object is floating, there must be other forces at work. The other forces at work are buoyant force. And what they do is these objects push on back on that object. Okay, so, and you think about this, Newton's third law, for every action there's an opposite and equal reaction. This object is interacting with the water. Those are two different things. So the box is being pulled in the water by the earth, applying a force to it, and the water also at the same time is also applying a force back. And depending on how dense something is, it'll either sink or float, or be way on top of the water, or completely submerged. It really depends on the density of the object compared to the density of the fluid. Okay, and even you can think of gases. If you have a hot air balloon, right? So if we make a little balloon here, they float, right? The reason they float is because of density. They take helium and they fill this balloon up, they heat the helium, and that causes the density of the helium to change, and then the air surrounding the balloon has a certain density. This density is less, so it causes the balloon to go up. Then when they want it to come down, they cool it off, and the balloon will come back down. That's the importance of density in a fluid. And you think about a fluid, if you realize it's a gas, then we're walking around in a fluid. So we're interacting with the environment. Now gases themselves, the forces they're applying aren't as great as, think of like a fluid like water. Okay. Now the force you've kind of been alluding to or talking about is buoyant force. And buoyant force is a force applied by fluids upon objects submerged within the fluid. So in our atmosphere we have nitrogen, oxygen, carbon dioxide, different types of gases. We're submerged in them, but they're very spread out. So the impact they have is very low. Okay, but when you think about a liquid like water, those things are a little bit closer together, almost like a solid, so they have a much greater effect. And we call that force that that acts opposite gravity on an object submerged or placed into a liquid or a gas, we call that buoyant force. Okay, and it opposes, like I said, the force of gravity. And this can cause some objects to float, and that is based on the density. So if this thing is not very dense and the forces that's being applied from the liquid is greater than the force of gravity, it floats. And we kind of talked about that. So there's some conditions. So if the force of gravity is greater than the buoyant force, F of B, what happens is it sinks. If the force of gravity is less than the buoyant force, F of B, it floats completely, way up on top of the water. It's not even in the water. And then if they're equal, it kind of just is submerged, kind of floating, kind of sinking, but never going too far into the water. They're kind of, they cancel each other out. They're like in equilibrium. So the object, if we were going to show you what it would look like, so if we had a pool and this was the condition right here, and we put the little water in there, then the box would be just like this if it was a box of something, because the force of gravity, F of G, and the buoyant force, F of B, which opposes the force of gravity in a fluid, are equal. So it'd be just submerged. Okay. Now, Archimedes' principle is what we've been talking about. We looked at the Syracusia. We looked at some other ideas about, if you put an object into something, it displaces a certain amount of fluid, and then that tells you the buoyant force of it. So if we had a pool like this, and if we went back a little bit here, I'm going to erase this stuff real quick. So if we went back to this thing, this pool right here, okay, and we had this much water in it, right? And we could measure where the water is. So we could say it's this high. There's this much left. Let's say it was 1 meter, 1 m. And then we put a box, we had a box over here. We took that and we threw it in there. The box then is submerged in the water. Okay. And then this might come up. It might come up 1/2 meter. So then we know that the water that it displaced is 0.5 meters, okay, cubed or whatever. That's its volume that it added. And then we could take the mass of that water, and we would see that if we weighed that water, that its mass would be less than the mass of this. So that means the force of gravity is greater, and it sinks. If we had a different condition, though, if we did something where the box was just like this, okay, where it's just below the water, kind of floating, kind of almost sinking, and we took and saw the water was 0.5 again, it went up 0.5, and we took the mass of this water, we would see it's the same as the force of gravity is applying to this. They're equal to each other. And the final condition we could have is if we, same box, maybe not the same, but a different box, and it was completely above the water. You've seen things do this, like a mattress in a pool. And we put this in here, and it displaced a certain amount of water, and we took the mass of this. We would see the mass of this is greater than the mass of this, so the buoyant force is greater than the force of gravity, and that causes it to float. And that's really based on Archimedes' principle. And we can just figure out what is the buoyant force by seeing the amount of water displaced. Okay, it's a kind of a simple way to say that. And then I've shared a few of these equations with you. Let's look at a few of these. And I might add some at the bottom here. But we have this one, F of G equals F of G times the displaced fluid equals the mass of the fluid times gravity. Okay, minus the submerged object's, mass. But if you remember, I kind of gave you a few of these, and one of them is F of G, and these are all derived from this one. So we could say, if we wanted to, we could say So we could say, taking this equation, and don't worry too much about this, we come up with this one first, force net. Because really what we have working here when we look at these boxes, we have a force down, a force up, and how does that all equal out? Well, we can figure that out with a couple equations. The first one is force net, and I've kind of showed you this in your on the equations I gave, and you've had these in your equation book already, but it's mass of the fluid times gravity. So if we know how much was displaced, and then we minus that from the mass of the object times gravity, that'll give us the force net. We can figure it out. How much water is displaced, times that by gravity, then we minus the actual mass of the object on a scale times gravity. That tells us the net force, whether it sinks, floats perfectly, or is pushed out of the water. Okay, that's the first equation. Another important one, kind of a derived from this one, is I'm just going to say f of n. And we take the equation for density and we get rid of this, the m, and replace it with something else. So if you remember, density is P equals m mass divided by v. So if we rearrange it to solve for m, we see m equals P times v. And then we take these two things, substitute them in for mass. Because say we don't know the mass, but we know the density of certain objects, right? It's easy to figure out the density of copper, the density of water. That's something that's a known. We don't even have to do any calculations. And then we also can figure out the volume of something pretty easy. Okay, so maybe it's easier, instead of figuring out the mass of something, maybe if we just know the volume, how much there is, then we can substitute those things in for mass. So P of F, V of F, and then we'll talk about gravity here in a minute. We do the same thing for this mass. So P object, V object. But then you see gravity's by both, so we just take these out. And we times it at the end by gravity. So we get rid of one of these timesing here. So the chance of making a mistake is less, a little bit easier calculation. Okay, so that's another way to look at this equation. The final one, and let me see if I can put it over here. Erase here, and we'll be done with these notes. So the final one is really derived from this one, and it's kind of a long way to derive it, so I'm not going to show you, but make sure you have this one and we'll use it in class. So you take this equation, keep rearranging it, substituting, and we can end up with this. The force of gravity, okay, on the object, and that's mass, right, times gravity, because it's a force, right? Okay, so, and then we divide that by, put that over the buoyant force, okay, and then that's equal to the density of the object divided by the density of the fluid. Okay. Okay, and I also want to add one more thing. You're going to see this term. It's not in these notes, and I kind of want to add it. And that's something called apparent weight. Let me write that. Let me get rid of these equations here. So apparent weight is a weight that's really not the weight of something. So apparent, hopefully I can get better at writing these. And my writing. So we all know what the weight of something is, right? We just take its mass. We figure that out on a scale. We multiply that by the acceleration due to gravity, and it tells us the weight. Force times, or the gravity times the mass. Apparent weight is something different, and it has to do with the fluid. Let me show you this, and we're going to have a problem like this too. So, so if you have like a block of lead, and you tie it to a spring scale, hang it in the air, and you get a force acting on it, might be 6 newtons. Okay, and then it's like G newtons, 6 newtons. But then if we take this same thing and we put it in a fluid, because of the buoyant force that acts on these objects, then we might instead in the fluid get 4 newtons. Okay, and that's what the apparent weight is really talking about. Okay, and then if we kind of know, what's really helpful though is if we kind of realize that this helps us figure something out, and that's the buoyant force, right? F of B, because if we know the weight of this is 6 newtons, and we know the apparent weight when we submerge it in that object is 4, then we know there must be 2 getting canceled out some way, and that 2 newtons it's canceling it out is the buoyant force. Okay, so that, like when we use that one equation I showed you there a minute ago, hopefully you wrote that down, but that can help us figure out the buoyant force, or F of B. So keep that in mind. I'm also going to record a problem for you from the book, and let me know if you have any questions. These notes were kind of long. Hopefully they helped you.